Welcome to the next lecture in the NPTEL series of lectures on Haskell. In this lecture, we will look at recursive data types. We have already seen user-defined data types, which you declare using the data keyword, right? You have something like data shape equals circle, double, or square double, right? This is the kind of thing that you can do with user-defined data types. Now, we would like to look at what happens if the data type is recursive, which is the most normal use case. Okay, so just like we have recursive functions, we can also have recursive data types. A recursive data type is one where some components are of the same type T. Okay, so that is basically it. So some constructors of a recursive data type have T among their input types as well as the return type, because remember, no matter what, the return types will be T, right? Because if I have something like data shape equals circle, double, square double, if you look at the type of circle, it will be double arrow shape. Square also has the same type, right? So you have a situation where the constructors have return type T, where the type that you are defining is T, but sometimes there is nothing that stops circle and square from having a shape as an input. Okay, and in general, not circle and square, but in a general constructor from having a shape as an input or the type T as input, and that is when you have a recursive data type. Here is the simplest example of a recursive data type, which you can define. Let's say we are defining natural numbers. Okay, so Haskell by default offers integers, but we can define natural numbers. What's a natural number? It's either 0 or successor of another natural number. That's it. Okay, so these two are constructors. Yeah, so you have two constructors. And 0 has type nat, successor has type nat arrow nat. That's clear, right? Okay. So let's so in this lecture, as I present the material, I'll also program in GHCA. I'll also program these and try to see what the results are in GHCA. You can do various things with nat now. You can check whether a number is a 0. Okay, and this doesn't require anything more than pattern matching. So is 0 of 0 is true, is 0 of anything else is false. Okay, good. So let's try this. Let me go to GHCI. I shall create a new file called temp.hs. I already have a temp.hs. I'll create a new file. Okay. Okay, I can start doing nat. Okay, data nat equals 0 or successor of nat, and is 0 of 0 equals true, is 0 of anything else is false. Okay, so this is something that I can do, and let's just check that it works. Yeah, so I can ask for the type of 0, it is nat. I can ask for the type of successor, it is nat or nat. Okay, now it's a little bit painful to write a natural number because I have to write successor of 0, and what do we expect the result to be? We expect to get an error because because nat has not been defined to be an instance of show. okay. So you will get an error. So you have to first say deriving show, then you have to also say deriving EQ if you want to actually use some equality, the equality relation on natural numbers, okay. Good. So let's just say deriving show. Now you can see that now you can actually ask for what is successor of 0. Sure, it just prints an internal representation of successor of 0. Okay. Now we might want to actually implement the is0 function in a different manner. We might want to just say is0 of n is0 prime, let's call it, is nothing but n equal to 0. Okay. Or if you want to use sectioning, we might want to just say is0 prime is nothing but asking whether your input is equal to 0. We could do this. Let's try to load this new program in GHCI and you will get an error. Why? Because we are using the equal to symbol. That cannot be used. Okay. And the way to fix it would be to say that not only deriving show but also deriving EQ. Okay. So almost by default you would mostly do deriving EQ show for almost all data types that you define. Okay. Except even in this case we will show that it might be better to do your own show, a custom show. Okay. But let's just check that we can reload this. Okay, it compiles well without a problem. We can ask is 0 prime of 0. Yes, you get true as you expect. Is 0 prime of successor of 0 should give you false as you expect. Okay, fine. So let's return to the slides. Okay, so this is how you check for use pattern matching to check if a natural number is 0. You can also define other functions like predecessor, okay, or previous number. I'll call it prev. Prev of 0 is 0 because we are only talking about natural numbers and there is no -1. Prev of successor n is n. Okay, you can define this. You can define various other things by primitive recursion, okay. Plus m0, you can do recursion on the second argument. Plus m0 is m, plus m of successor of n is successor of plus mn. Okay. Note that in the recursive call, this plus is being applied on m and n, which are smaller arguments, right? In the definition, plus is being applied on m and successor of, plus is being defined on m and successor of n, and the definition involves the application of plus on m and n. Okay, so that's a proper recursion. Okay, and this tells you that this is like recursion on lists or whatever. Recursion need not be on smaller numbers, okay, because we are not talking about numbers, we are talking about some kind of data type. Okay, simpler data values is what we want, and a priori it is clear that successor of n is a more complex data value than right. That's very clear because just you use more letters for one, but also it is something applied on top, something applied on n, okay, whereas this is just plain n. Okay, so you're doing recursion on some kind of structure. Okay, so this is also called structural this is not something new, we are already familiar with it. Lists, okay, x colon x's is some structure, it's a more complex structure than x's. Okay, and in defining some function f on x colon x's, you use the value of the function f on x's. Okay, so that's what is happening here. Okay, you can also define multiplication. Mult m of 0 is 0, mult m of successor of n is plus m of mult mn. You can do all this, but what happens is that when you try to compute all this in GHCA, you will get some big successor of successor of successor of successor of 0 kind of representation. So one thing you can do is to define your own custom show. What you do is you just turn your nat into int, the inbuilt int type. So turn to int 0, the 0 with the capital Z, that is just the number 0. Turn to int of successor n is turn to int of n plus 1. Okay, let us try to program all this in and let us see how what results we can see. Okay, so let's let me go back here. So rather than having rather than deriving show, I will have a custom show. Instance show nat, where show of 0, show of n, show equals show applied after turning the number to int. Recall that dot means function composition. Okay, you first apply turn to int on your nat value, it will turn it into an int, and then you do show. The left hand side show is of type nat arrow string that we are defining. The show on the to the right of the equality symbol is of type int arrow string, which has already been defined by the Haskell system for us. Okay, and this turn to int could be or I could just say nat to int, and nat to int could just be a standalone function in itself. It has enough utility, so let's just do that. Nat to int of 0 is just the numeral 0, which belongs to type int. Nat to int of successor of n is nat to int of n plus 1. And we had better give a type here, just be safe. Actually, we could even just say nat to integer, it needn't be just int. Okay, so that's this thing. Okay, good. So now we can actually do the other functions that we had defined. Successor of or I could call it something next previous. Since I am calling it previous, I am calling it next. Yeah. So next is nothing but the successor constructor. Previous is defined by pattern matching. Previous of 0 is 0. Previous of successor of n is just n. Okay, and then you can have add mult, which are of type nat arrow nat arrow nat. And add of m0 is m, add of m successor of n is successor of add mn. Mult of m0 is 0, mult of m successor of n is add of m of mult mn. Okay. So you are defining multiplication in terms of addition, but also in terms of multiplication of m with a smaller number. Okay, smaller number here is structural recursion. Successor n is a more complex term than n. That's all you want to care about. Okay, so we have done all this. We could actually now go and test all this. So the only thing that is lacking is to turn something from integer to natural number, because now I have to give, I should say add of successor of 0. This is for 3 with mult of successor of 0 with, you have to give your own long term. Okay, so essentially we are saying 3 plus 2 into 3. So that should be 9, the answer. Okay. Because I have to reload. Okay. Okay, I get the answer 9 displayed, but now it's painful to write successor of 0. So what you might have to do is to write a function that converts from int to nat and then do this. Okay, but then if you do that, it doesn't look any different from actually working on integers directly. Okay, so as I mentioned, in this show equals show dot turn to int, the left show has type nat arrow string, the right show has type int arrow string. Okay. Okay. So now nat was one recursive type. You can have recursive types that can also be polymorphic. List is a very canonical example. List A is a list of elements of any type whatsoever. It's either nil or cons. Let's call the colon, we will call it cons. Cons are applied on A and a value of type A and a value of type list A. Okay. This is just the built-in type list A, but if you define it yourself, you can actually add some features of your own, right? For instance, you can define functions as usual on pattern matching, head, tail, etc. Head is a function of type list A arrow A. Head applied on cons x underscore is x. So actually now in built-in Haskell head and tail, Haskell always produces a warning, but I can write my own head and tail. Let me do that now by declaring list as a new data type. Data list A is either nil or cons. Cons stands for construct, applied on a value of type A and a value of type list A. And okay, I could show this, but then once again, just like natural numbers and so on, I can define a custom show, right? I can say instance, the first thing I can do is show list is nothing but left brace followed by actually you could just do this. Show of a list is just show of make list L. Okay, what is make list? So let's do this. Is of type list A, where list with a capital L to the built-in list type. Okay, that's all. Is X followed by make list of X's. Right, so you can move between, you can also move the other way, you can move from a Haskell list to your new capital L list data type that you have defined, except now you can actually tailor some of the functionality in the this thing. So you could, for instance, say head of empty list is, you can explicitly give some error message, okay, or you can give a maybe value, yeah, that's an option. So you can say head is of type list A arrow maybe A, okay. So these are all things that you can do. Tail also similarly is of type list A arrow maybe list A, or you can say tail of empty list is empty list, okay. You have lots of freedom there, okay. So so actually I will give it a better name, to built-in list. I will say H list stands for Haskell list, let us say, the built-in Haskell list. Right, and then similarly you can do a from H list. And now you know that Haskell lists you can apply fold, etc. So the nice way of defining a capital L your own list type from a Haskell list is to actually say fold R of start with nil and keep applying cons, right. So that's very nice, okay. So this is a thing that you can say, okay. Okay, so right, so you can do all this. Let's get back to the slides. You can fix your head function with a custom head. You can say list A arrow maybe A, head of nil is nothing, head of cons X, whatever is just X. Similarly, you can do for tail. But we had a fold for the built-in list. You can come up with a fold for your own list also, because one of the, if I go to GHCA and if I just ask for certain types, it won't show lists, it will show foldable for certain things, okay. Foldable is a type class, okay. It's a type class. It is not just a type class, it is a, just like, so you have ORD, enum, numeric, EQ, etc. are all type classes. They constrain types. Now, foldable is a type class. That is a collection of type constructors. Okay. So, you can have type classes that are a collection of types, but you can also have type classes that are a collection of type constructors. Okay. What you are saying is list is a way of forming a new type from existing types. Now, this list, which is a type constructor, can be of type foldable, which means that the collection type that you create using this constructor, you can apply fold on it, okay. And to make something an instance of foldable, all you need to do is just define foldr on that, and the foldr definition is just exactly the same. Recall that the foldr definition for the built-in list was this: foldr f v, the empty square brackets equals v, foldr fv x colon xs equals fx folder fv xs. Instead of colon you use cons, and instead of the empty square bracket you use nil. Okay, that's all. Okay, and this has also been made a foldable type, and now you can use folder both in one direction and in the other direction. Let me actually show it in the code for you. Okay, so you defined your own list, you made instance show list, etc., and this make list won't compile. You have to say from h list to h list. But even before that you could say, let's say it here, instance foldable list, where folder of fv nil equals v yeah. So that's it. Okay, now once you have done this, you can actually say to h list is also folder, you can use folder of, instead of cons you use the colon operator, and instead of nil you use the empty square brackets. Okay, so this is something that you can do, but with some modified behavior. You can say head and tail are of return type maybe a. Okay, right. So this is it. So you can test it, of course. So you can, I'll reload this. There is an error, expecting one more argument to list. Yeah, so you should say instance show list A. List itself cannot be show because list is a type constructor. List A is what can be of type show, but then for this to be of type show, A itself has to be showable. Okay, so you have to say instance show A implies show list A. I'll first check if this compiles. If it doesn't, then you will have to add that. Okay. Yeah, so there is no show A. So what you should do is, your list A can be shown only if values of type A itself can be shown. So what you should do is, instance show A implies show list A. Okay, so this is how you should do it. Let's go back and check what if it compiles. Now it compiles. Okay, so yes, so we have this. So I could just say cons 5 of cons 7 of nil, and I will get the output 5 7. Okay, because it's converting it to a list and showing that list. Okay, fine. So okay, so let's return to the slides. Right now I can do list sum, for instance, and I can say once the moment I do fold R, every other definition is available to me, all other folds. So I can do fold L prime, for instance, and list sum, and this is a list A, not not the built-in list given by square bracket A. Okay, so you can still use fold L prime and all variants on this. Okay, good. So we can test this. Rather than fold L prime, I'll just try to use fold L. Okay, so I'll let's just say list int. Yeah, and this should work automatically, okay, because you have defined your own definition capital L list to be of type foldable, okay. So let's save this. Let's try to run this in GHCI and see if it works. Let's first see if it compiles. It does compile, and I can do list sum of, and now I should give a list in my style. I should in this style cons of 5 of cons of 7 of, okay, 7 of cons of 67 of nil. Okay, you will get the correct value. Okay, 5 plus 7 plus 67 is 79. Okay, let me get back to the slides now. Okay, so we have seen natural numbers, we have seen lists. Okay, now we'll look at some more complex data types, recursive data types.